Hi everyone, my name is Boyang. Today I'm going to present our work, A Principled Approach to Model Validation in Domain Generalization. This is a joint work with Tuan Wing, Matthias Schulz, Prakash Ishwar, and Suchin Aaron. This work is sponsored by the Air Force Office of Scientific Research and NSF. In this paper, we revisit the traditional model validation method for domain generalization, identifying the shortcomings of the traditional method, and propose a new one. So first, what is the domain generalization problem? So the typical domain generalization problem is as follows. We are given a bunch of labeled samples from several scene domains, and our goal is to learn a classifier that can generalize well to unseen domains. For example, in this figure, our training data is composed by the figure from 3 scene domains: sketch, cartoon, and art painting. But our test data is from a completely new unseen domain, which is photo. And as we can see, the training data and test data doesn't share the same data distribution since they have very different figure style. This phenomena is called distribution shift, which is also the biggest challenge of domain generalization problem. To address domain generalization problem, a typical DG methodology is to learn domain invariant feature by a representation function f that map from the input space to the representation space, and jointly train a classifier G that map from the representation space to the label space. This workflow can be seen in this figure. Given the data from scene domains, we want our representation function f can extract domain invariant features. By saying domain invariant features, we mean that this feature should be shared by all scene domains, not only one scene domain, but all. And here we identify the shape should be the invariant feature. And then we train a classifier G to do the prediction. This workflow can be summarized in the equation 1, that our training loss is composed by the classification risk and domain discrepancy loss. In practice, we denote the classification risk as equation 2. Well, for domain discrepancy, though there are many choices to quantify this loss, the main idea stays the same. First, we need a measure to quantify the discrepancy between domain distributions. And since we want our F can extract domain invariant feature, thus we hope the discrepancy of the joint distribution in representation space of the unseen domain and seen domain should be small. Okay, thank you. After getting some basic idea of domain generalization, next, my collaborator Tuan will present the remaining work. Okay, thank you.
Thank you, Bozan. Hello, my name is Tuan Nguyen. I'm a postdoctoral researcher at Tufts University. I'm working on information theory, machine learning, and signal processing. And in this slide, I will talk about the first contribution of our work, which is the fundamental trade-off between the classification risk and the domain discrepancy. First, let me introduce a new notation, T delta. T delta is the minimum value of the domain discrepancy under the constraint such that the classification risk is smaller or at most a value of delta. And in here, if the domain discrepancy measure D is a convex function on both its argument, then for any classifier G, we show that T delta is non-increasing and is convex. And in here, if we denote the x-axis by the classification risk, and we use the domain discrepancy as the y-axis, then here is the curve of T delta in the red color. For a given mapping F and classifier G, a point here is a pair of the classification risk and the domain equivalency. And we can see that on the point here stay above the 9 of t delta due to the definition of t delta, the minimum of the domain equivalency. Therefore, we cannot find a mapping F to achieve this point, which can perfectly minimize both the classification risk and the domain equivalency. Therefore, we say that there is a fundamental trade-off between minimizing the classification risk and the domain equivalency. We cannot minimize these two terms perfectly at the same time. This trade-off is well considered on the training phase, but is ignored on the validation phase. For example, here for the training phase, most of the methods train a loss function have two terms. The first term is the classification risk, and the second term is the domain equivalency. And we can control the trade-off between these two terms by controlling the value of beta. However, on the validation model section phase, most of the methods select a model that have the minimum value of the classification risk and ignore the domain equivalency. And we know that because if a model aims to achieve a small value of the risk by the trade-off, it may produce a high value of the domain equivalency, and due to the distribution, this model may not work well on the test data with different distribution with the validation data. So given that limitation, we propose a new method that select a model based on both the classification risk and the domain equivalency. So the new validation loss function have two terms. The first term is still the classification risk, and the second term, the new term is a domain equivalency term. We use two hyperparameter alpha and beta to control and combine the two objective functions with different scales. And in practice, we use the cross entropy as a classification risk, and we use the maximum mean equivalency as a domain equivalency, and we use beta equal 1 and alpha equal by 2. We test this new validation method on 3 data sets and 12 steps of that algorithm, and compare with the current validation method in domain generalization. So on the PACS dataset, our new method can improve the accuracy of 7/12 tested algorithm compared with the traditional validation method. On the VLCS dataset, we can improve the accuracy of 8/12 tested algorithm. And for the CMNIT dataset, our method can improve the accuracy of 9/12 tested algorithm. This demonstrates the effectiveness of our new validation model selection method in domain generalization. Thank you so much for the listening. If you have any questions, so feel free to let me know. Thank you. Bye.